The next point is the expression for the capillary rise or fall. For that there are two methods, using pressure difference and using forces. We will discuss the first method, that is using pressure difference. We will find the rise in the liquid level, that is H. Here is a diagram. In this diagram there is a container. Inside the container there is a liquid, and in the liquid the capillary is deep. As soon as the capillary is dipped inside the liquid level rises in the capillary. The capillary rise or fall is observed due to the pressure difference across the curved surface. Consider the rise of the liquid like water as shown in the figure. The density of the water is rho and radius of the capillary is small r, and the height of the liquid or the water inside the capillary is denoted by letter small h. The surface inside the capillary is concave. Here is the concave surface. Thus there is a pressure difference between the two sides of the top surface. This pressure difference, it can be given by Pi minus P0 is equal to twice T upon R. This equation shows that the pressure of the water inside the tube just at the meniscus is less than the atmospheric pressure. As shown in the figure, there are 2 points A and B. These points, they are at the same level, and therefore the pressure at these 2 points is the same. That is, PA is equal to PB. PA is the pressure at point A and PB is the pressure at point B. Both are at the same level, and therefore we can write PA equal to PB. But what is PB? The PB is nothing but P0, that is the pressure which is below the meniscus, and H rho G, this is the pressure of this much liquid column. Therefore P0 plus H rho G is equal to PA, and it will be equal to PI. At the equilibrium, PA will be equal to PI. Pressure at point A, it will be equal to pressure above the liquid column. Therefore Pi minus P0 is equal to H rho G, where H is the height of the liquid column, rho is the density of the liquid, that is water, and G is the acceleration due to gravity acting on the liquid column. Therefore we can write Pi minus P0 equal to H rho G. This is the equation number 2. From equation 1 and 2, what is Pi minus P0 is equal to twice T upon R. This is the equation number 1. And Pi minus P0 is equal to H rho G. This is the equation number 2. From both the equation, we can write twice T upon R is equal to H rho G. From this equation, we can find the value of H. If theta is the angle of contact, in this diagram we can see the theta is the angle of contact. Here is the meniscus, and this is the wall of the container, wall of the capillary tube. The angle made by this tangential force with the wall of the container is called as the angle of contact. From this angle of contact, we can write small r is equal to capital R into cos of theta, and capital R is the radius of the curvature of the meniscus. Using this equation, that is the equation 4 and 3, this is equation 4, r equal to small r upon cos theta, and equation 3 is, this is the equation 3, twice T upon R equal to H rho G. We can substitute R, small r upon cos theta. We get twice T cos theta upon small r is equal to H rho G. Therefore H will be twice T cos theta upon rho G R. This is the expression for the capillary rise for a liquid. From this equation, we can relate H and R. H is inversely proportional to the R, that is the radius of the capillary tube. For the smaller radius capillary, there will be high level of the water inside the capillary tube. Means radius is small, the height of the liquid inside the capillary will be larger, and if the radius is greater, the height will be lesser. In case of the liquid like mercury, there is a convex meniscus. The angle of contact, that theta, will be obtuse angle, and for such a conditions, for the mercury like liquid, the cos theta is a obtuse, that is cos theta will be negative, and therefore the H will be less. Therefore cos theta is negative, and so for H there is a decrease in the level of the liquid inside the capillary tube. Means when theta is the obtuse, that is the angle of contact is obtuse angle, then there will be fall in the liquid level inside the capillary tube, or we call it as a diffraction inside the capillary tube. Now the second method, so as to find the height or the diffraction, that is the rise or fall of the diffraction inside the capillary, is it is by using the forces acting on the liquid column. Now in this diagram we can see there is a container. Inside the container there is a liquid, and consider a glass capillary tube of radius r is dipped into the liquid which wets the glass capillary. That is, the liquid is like a water. The liquid rises into the capillary to a certain height, that is small h. This is the height of the liquid inside the capillary. If T is the surface tension of a liquid, a force of magnitude T acts on each unit length of the liquid surface which is in contact with the wall of the capillary. This force is tangential to the surface of the liquid. Now look at this force T. It is tangent. It is tangent to the liquid surface inside the capillary. This force is tangential to the surface of the liquid at the point of contact and directed inwards. The direction of the force is inside the liquid column from all sides. Suppose theta is the angle made by the tangential force. Now this tangential force makes an angle of theta with the wall of the capillary tube. According to the Newton's third law of motion, the reaction force equal but opposite to the tangential force T acts at a point of contact, and it is directed away from the, it is directed outward. You can say it is directed outward. Now this will be the reaction force and this will be the tangential force. Both the forces, they are opposite to each other. Now we can resolve this force T. This tangential force, it can be resolved. How it can be resolved? The tangential force can be resolved into rectangular components. First one is the T cos theta. In the diagram we can see the T cos theta, which is in the upward direction, and it is along the wall of the capillary tube. This is the T cos theta on both the sides. And there is another component, that is the T sin theta, which is the horizontal component and perpendicular to the wall of the capillary tube. These are the two components, T cos theta and T sin theta. T cos theta and T sin theta. Now if we consider the entire circumference of the capillary bore, this is the capillary and this is the capillary bore, and if we consider this entire surface of the capillary bore, it will be a circular part and it has a circumference 2 pi r. All the horizontal components cancels each other. The horizontal component is T sin theta. This is T sin theta. This component is also T sin theta. All the horizontal components, they cancels each other because they are opposite to each other, and therefore T sin theta cancels T sin theta. In this way all the horizontal components, they cancels each other. Only the vertical components are there, and these vertical components add to each other, and hence there is a resultant upward force. We can see these arrows. These arrows indicates the upward force, that is T cos theta component per unit length of the liquid surface, which is in contact with the wall of the capillary tube. Therefore, the total length of the surface of the liquid in contact with the wall of the capillary is equal to the circumference of the cross section of the capillary, and therefore we can write the total upward force on the liquid column inside the capillary tube is F equal to twice pi r t cos theta. Due to this upward force, the liquid column rises inside the capillary tube to the height h. This is the main reason. Due to this upward force, the liquid column rises inside the capillary tube, and in the equilibrium, the upward force is balanced by the weight of the liquid column, and therefore we can write this upward force, that is F, that is equal to 2 pi r t cos theta, is balanced by the weight of the liquid column, that is mg, where m is the mass of the liquid column, and g is the acceleration due to gravity. Rho is the density of the liquid. Therefore, we can calculate the mass of the liquid column. M equal to rho into V. This is the general formula. Mass is equal to density into volume. Now, what is volume? If the liquid column is cylindrical, therefore we can write volume equal to pi r square h, because r is the radius of the liquid column, radius of the capillary, and h is the height of the liquid column inside the capillary. Therefore, we can write m, that is the mass of the liquid column, is equal to rho into pi r square h. Now, from the equation 1 and 2, we can write, what is equation 1? Here is the equation 1. F equal to twice pi r t cos theta equal to mg. या m च्या ठिकाणी आपण आत्ताची व्हॅल्यू टाकणार आहे. This is the value of m. M equal to rho pi r square h. We get 2 pi r t cos theta is equal to rho into pi r square h g. And from this we can calculate the value of t. T equal to r g h rho divided by 2 cos theta. This is the expression for surface tension of a liquid, and this expression shows that the surface tension depends upon all these quantities, that is r, that is the radius of the capillary, small g, that is acceleration due to gravity, h is the height of the liquid inside the capillary, rho is the density of the liquid, and theta is the angle of contact. And the rise of the liquid inside the capillary can be written from the above equation, and this rise, it can be written as h, that is equal to twice t cos theta upon h rho g. This will be the equation for height, rise of the liquid in the capillary tube. This height or the rise, it also depends upon the surface tension of the liquid, angle of contact, radius of the capillary, acceleration due to gravity, and density of the. From this equation, we conclude that rise of the liquid in the capillary is inversely proportional to the radius of the tube and density of the liquid. H आणि R आणि rho मधले रिलेशन आपल्याला सांगता येईल. H हा R आणि rho बरोबर इनवर्सली प्रोपोर्शनल असतो. या पद्धतीने आपल्याला एक्सप्लेन करता येईल. The height of the liquid is measured horizontally. Now this is the meniscus. This is the container. There is a water or the liquid in the container. Capillary is dipped inside the liquid, and there is a rise of the liquid in the capillary tube. This rise is denoted here by letter H. Now this rise in the liquid level inside the capillary tube, it is measured from the bottom of the meniscus, that is H. But there is some liquid above this level in the meniscus, hence the height should be corrected. This correction is H equal to H plus R by 3. Since H is greater than R, that is height is greater than R. Because for the capillary, the R is in the order of 1 millimeter and H is very moderate. And therefore we can say H is greater than R. We can neglect R by 3. For the water, angle of contact is 0 degree and density is 1 gram per centimeter cube. We can write the equation for the surface tension, and that will be T equal to HRG upon 2. This is the discussion regarding the capillary action. Thanks for listening.